Somewhere inside your Achilles tendon right now, there are collagen molecules that are almost as old as you are. Not metaphorically old, actually old. Scientists proved this using a strange method borrowed from nuclear history. They measured carbon-14 left over from Cold War bomb tests, which spiked in the atmosphere in the 1950s and 60s and slowly settled into every living tissue on Earth, including yours. When researchers in Denmark, led by Katja Heinemeier, dated the core collagen inside adult human tendons using this bomb pulse signature, they found something almost nobody expected. The deep, load-bearing collagen fibers in the middle of your tendon are barely replaced at all after you finish growing. Muscle rebuilds itself every few weeks. Skin replaces itself in about a month. But the core of your tendon, the actual rope that connects muscle to bone, mostly just sits there, unchanged, for decades. So here's the pattern interrupt, before you assume this is another drink more collagen powder video. This isn't about supplements as a magic fix. And it isn't about some detox trick for joint pain. This is about a genuinely strange piece of biology that explains why tendons feel like they never truly get stronger, no matter how much you train, why they seem to betray people the moment they finally get into good shape, and why the entire way most people try to strengthen a tendon is built on a misunderstanding of what strength even means for this tissue. By the end of this, you'll understand exactly what is physically changing inside a tendon when it does adapt, why that process looks nothing like muscle growth, and what that means for how you should actually load your body if you don't want to be the person icing their knee at 45 wondering what went wrong. Let's start with the basic confusion, because almost everyone carries it around without noticing. When you think about getting stronger, you're almost certainly picturing a muscle. You picture fibers tearing under load, satellite cells swarming in, protein synthesis ramping up, and within days that muscle is measurably bigger and firing more force. This is real, it's well documented, and it happens on a timescale you can feel. Soreness on Tuesday, a size difference by next month. Tendons don't work like this, and the mistake almost everyone makes is assuming they do. A tendon is not a smaller, less exciting version of a muscle. It's a completely different kind of material, built for a completely different job, and it adapts using a completely different clock. Think about what a tendon is actually for. A muscle's job is to contract and produce force. A tendon's job is to transmit that force to bone without stretching so much that the movement becomes mushy and imprecise, and without snapping under sudden peak loads, like when you land wrong off a curb or sprint out of the blocks. To do that job, a tendon is built almost entirely out of a protein called type I collagen, arranged into parallel bundles, like the strands of a climbing rope twisted together for strength. That rope-like structure is the first thing worth holding on to, because we're going to keep coming back to it. Now here's where the Heinemeier finding becomes genuinely important rather than just a fun trivia fact. If the core rope of collagen fibers is barely being replaced in adulthood, that means a tendon cannot get stronger the way a muscle does, by breaking down old material and rebuilding fresh material in greater volume. There isn't much rebuilding of the core happening at all. So when your knee tendon or your Achilles does adapt to training, and it genuinely can, the adaptation has to be happening somewhere else, through some other mechanism. This is the part most people never get told, and it's the part that actually matters if you want to understand why tendon injuries behave the way they do. So where does the adaptation actually happen? Around and between those thick collagen ropes, there's a much thinner, much more active layer of tissue, the matrix and the cell population living inside it, called tenocytes. Danish physiologists Michael Kjaer and Peter Magnusson spent years studying this using a technique called microdialysis, essentially inserting a tiny probe directly into the tendon tissue of living volunteers to sample what's happening biochemically during and after exercise. Their work, done largely at the University of Copenhagen through the 2000s, showed that after a bout of loading, tendon tissue does ramp up collagen synthesis. But locally, at the edges and in the surrounding matrix, not by demolishing and rebuilding the entire core rope. It's less like replacing a cable and more like reinforcing the sheath around it, adjusting the cross-links between fibers, changing the water content of the matrix, subtly altering how densely packed and how aligned those existing fibers are. Here's the part that reframes everything, so stay with this one. Tendon getting stronger mostly means the existing rope becoming better organized, better cross-linked, and stiffer, not becoming a bigger rope made of newer material. This is a fundamentally different kind of strength gain than muscle hypertrophy, and it explains a mystery that trips up a lot of otherwise well-trained people. You can spend months building visibly bigger, more powerful muscles while your tendons lag dangerously behind, still tuned for the weaker body you had a year ago. The muscle can outpace the tendon's ability to keep up because they're improving through entirely different biological processes on entirely different timelines, and those timelines are not subtle. Human muscle can show a measurable strength increase in as little as 2 to 4 weeks of consistent resistance training. Tendon stiffness changes, tracked using ultrasound-based methods in studies from groups including Kongsgaard and colleagues in Denmark, generally take considerably longer. Meaningful adaptation showing up more on the order of months, not weeks, and continuing to develop with consistent loading over a period that can stretch beyond a year for full remodeling of stiffness and cross-sectional area. If your training program assumes your tendons are keeping pace with your muscles because they're attached to the same joint, you are working with a false assumption baked directly into how you're progressing your loads. This is a natural moment to ask the obvious follow-up question, so let's ask it. If tendons adapt so slowly, why do so many tendon injuries? The aching Achilles, the cranky patella tendon under the kneecap, the tennis elbow that won't quit, show up not in beginners, but in people who've been training for years and are arguably in the best shape of their life? Shouldn't more experience mean a stronger, more resilient tendon by now? The answer lives in a model developed by Australian researchers Jill Cook and Craig Purdom, published in the mid-2000s, called the Tendinopathy continuum, and it is one of the most useful mental models in all of sports medicine because it explains why tendon pain doesn't behave like a typical injury. A muscle strain is usually a discrete event. A tear happens, you feel it, it heals in a fairly predictable window. Tendon problems are usually not a single event at all. They're the slow accumulation of a mismatch between load and capacity, moving through stages. In the earliest stage, called reactive tendinopathy, the tendon responds to a spike in load, a sudden jump in mileage, a new sport, a return from time off, by swelling slightly and increasing water content, essentially a short-term protective response, and if you back off, it can settle back down completely. If the mismatched loading continues, the tendon moves into a stage Cook and Purdom call tendon disrepair, where the matrix starts breaking down its normal organized structure faster than it can be repaired. Collagen fibers lose their neat parallel alignment, and small blood vessels and nerve fibers start growing into areas that shouldn't normally have them, which is part of why the area becomes painful and sensitive. Left unaddressed long enough, it can progress to degenerative tendinopathy, where areas of the tendon essentially become disorganized, weaker tissue that doesn't respond well even to appropriate loading anymore. Here's the detail that should genuinely surprise you, because it upends how most people think about tendon pain. Researchers including Karim Khan have pointed out for years that when you biopsy or scan a painful tendon in this disrepair stage, you often don't find the classic signs of inflammation you'd expect from an itis, a swollen, angry, red injury site. That's actually why the medical field mostly stopped calling it tendinitis and shifted to tendinopathy. Itis implies inflammation as the primary driver, and the tissue changes researchers actually observe are more about structural disorganization of the collagen matrix than a classic inflammatory response. This matters practically because it's part of why anti-inflammatory approaches alone often underperform for tendon pain compared to how well they work for something like an acutely sprained ankle. You're not dealing with simple inflammation to calm down. You're dealing with a structural material that has partially lost its organized architecture and needs a different kind of stimulus to reorganize itself. So let's return to the rope metaphor, because this is where it earns its keep. Picture a climbing rope made of many parallel strands. In a healthy tendon, those strands run cleanly parallel, tightly packed, transmitting force efficiently along their length. In disrepair, imagine some of those strands going slack, kinking, running at slightly different angles to each other, with some disorganized filler material stuffed between them. The rope still holds some weight. It might even look fine from the outside, but it's mechanically compromised, and here's the counterintuitive part. It doesn't get better with rest alone. A slack, disorganized rope doesn't reorganize itself back into tight parallel strands just by hanging there unused. It needs to be loaded again in a controlled and specific way to pull those strands back into proper alignment. This is the single biggest reason so many people mismanage tendon pain. Their instinct is to fully rest it, the way you'd rest a pulled muscle, and while short-term unloading can help calm an acutely reactive tendon, prolonged complete rest for a tendon already in disrepair often leaves it exactly as disorganized as before, just quieter. This is where mechanotransduction comes in, and it's genuinely one of the more elegant pieces of biology in this whole story. Mechanotransduction is simply the process by which a physical force gets converted into a biochemical signal a cell can respond to. Tenocytes, the cells living inside that collagen matrix, have structures that let them physically sense when the surrounding fibers are being pulled and stretched. When that happens, it triggers signaling pathways inside the cell. Baar's research group at the University of California, Davis has done extensive work mapping this out. That switch on genes responsible for producing more collagen and matrix proteins, and that also promote the enzymatic cross-linking that makes existing collagen fibers bond to each other more strongly. Without that mechanical pull, tenocytes basically sit in idle. This is the biological reason why loading, not rest, is the actual language a tendon understands when it needs to reorganize and strengthen. And this is the detail that separates good tendon rehab from bad tendon rehab. Not all loading speaks that language equally well. This is where a landmark comparison becomes useful. For years, the gold standard rehab protocol for Achilles tendinopathy was the Alfredsson eccentric heel drop protocol, developed by Swedish researcher Håkan Alfredsson in the late 1990s, which involves slowly lowering your heel off a step under load, repeated in high volume over 12 weeks. It worked remarkably well for many people and became a cornerstone of sports physiotherapy. Then, in 2009, Danish researcher Mads Kongsgaard and colleagues ran a comparison for patellar tendinopathy, the tendon under the kneecap. Testing heavy, slow resistance training, essentially controlled squats and leg presses performed slowly through a full range of motion under substantial load against the traditional eccentric protocol. The heavy, slow resistance approach produced comparable pain and function improvements to eccentric training, while patients in that study reported higher satisfaction with the process, likely because it felt more like normal, familiar strength training rather than an isolated, repetitive daily ritual. What both of these successful protocols share is the actual mechanism worth extracting: sustained, heavy, controlled mechanical tension applied to the tendon over a period of weeks, done slowly enough that the tissue is under real load for an extended time per repetition, repeated consistently enough to give tenocytes a strong, unmistakable mechanical signal to respond to. Fast, bouncy, uncontrolled loading, the kind involved in sudden sprints, jumps, or explosive changes of direction without any conditioning base, is a very different kind of stimulus. It can spike load past what the current matrix can absorb, which is exactly the mismatch that tips a tendon toward that reactive or disrepair state described earlier. This is not an argument against explosive training. It's an argument that explosive capability has to be built on top of a tendon that has already been conditioned with slower, heavier, sustained loading first. The equivalent of tightening and aligning the rope strands before you start whipping it around at speed. There's a second piece of research worth bringing in here, because it connects the biochemistry back to something people can actually control day to day. If mechanical loading is the signal, collagen synthesis still needs raw material and cofactors to actually build new matrix protein in response. Collagen itself is unusually rich in a specific amino acid profile, and vitamin C is a required cofactor for the enzymatic step that stabilizes collagen's triple helix structure. This isn't new information. It's the same biochemistry behind why historical sailors with vitamin C deficiency, scurvy, suffered from literally falling apart connective tissue. Baar's group, in a study led by Gregory Shaw and published in the American Journal of Clinical Nutrition in 2017, tested whether the timing of collagen-rich gelatin combined with vitamin C, taken roughly an hour before a bout of exercise, would affect markers of collagen synthesis compared to a placebo. They found that this combination increased blood markers associated with collagen synthesis compared to placebo when consumed shortly before the loading bout specifically. The loading and the nutrient timing together mattered more than either alone. This is a real, modest, mechanistically grounded finding. Not a claim that gelatin powder rebuilds tendons by itself, but evidence that giving the tenocyte machinery its raw materials around the same window as its mechanical signal appears to support the synthesis process the mechanical loading is already triggering. Let's pause and re-anchor, because there's a lot of mechanisms stacked up now, and here's the part most people still get wrong even after hearing all of this. They assume that once a tendon feels fine, day-to-day pain-free function, it has fully adapted and caught up to whatever new training load they're throwing at it. But remember the timeline mismatch from earlier. Tendon stiffness and matrix reorganization often lag months behind a muscle's strength gains and behind a joint feeling fine during normal activity. Feeling no pain is not the same as having completed structural adaptation. This is precisely why the classic injury story is so common. Someone ramps up training intensity, feels great for 6 to 10 weeks because the muscles and cardiovascular system adapted quickly and nothing hurts yet, and then the tendon, still working through its much slower remodeling timeline, finally reaches its capacity limit and fails, often described afterward as coming out of nowhere, when in fact the mismatch had been building the entire time. So now you have the actual physics and biology of the situation clearly laid out. A slow turnover core rope structure that mostly reorganizes rather than rebuilds. An active surrounding matrix that responds to mechanical signals through tenocyte mechanotransduction. A continuum model explaining how mismatched loading creates a spectrum from reactive irritation to structural disorganization. Evidence that sustained heavy loading reorganizes that disorganized structure better than rest alone, and evidence that nutrient timing can modestly support the synthesis machinery the loading triggers. Now let's turn this into what you actually do with it. First, if you're introducing a new activity, a new sport, or ramping up training volume, treat the tendon's adaptation timeline as the limiting factor in your progression, not your muscular or cardiovascular fitness. Concretely, this means increasing training load. Mileage, weight, jump volume, whatever the relevant variable is for your activity. By small increments over a period of months rather than weeks, even if your muscles and lungs feel ready to handle much more, much sooner. The tendon simply cannot be rushed onto the timeline your other tissues are capable of. Second, if you already have a nagging, dull, familiar tendon ache, the kind that shows up predictably after certain movements and settles with rest. Don't default to complete rest as your management strategy, and don't assume it's simple inflammation that anti-inflammatory measures alone will resolve. Based on the mechanism we just walked through, controlled loading is the actual stimulus that reorganizes disorganized matrix back toward aligned, functional structure. This looks like slow, heavy, controlled strengthening work for the affected tendon. Think slow squats for a knee tendon, or slow calf raises through a full range for an Achilles, done consistently over weeks, generally best guided by a physiotherapist who can judge how much load is appropriate for where that tendon currently sits on the continuum, since loading a tendon that's acutely reactive to aggressively can push it further into disrepair rather than out of it. Third, if you want to support the synthesis process during a structured loading phase, the research points to consuming a source of collagen-rich protein together with vitamin C in the window shortly before your loading session, rather than at some disconnected time of day. This is a modest, supportive input tied to a specific mechanism. It is not a substitute for the loading itself, and it will not do anything meaningful without the mechanical signal that switches on the relevant synthesis pathway in the first place. Fourth, and this is the piece that ties the explosive training question back together. Build your capacity for fast, high-force, elastic movement. Sprinting, jumping, rapid changes of direction. On top of a base of slower, heavier, controlled strength work for the relevant tendons, rather than jumping straight into high-speed loading with an unconditioned tendon. This is the practical translation of the rope needing to be tightened and aligned before it gets whipped around at speed. Athletes and coaches who build in phases of controlled heavy loading before ramping into plyometric or sprint heavy work are, whether they use this exact language or not, respecting the actual biological order of operations that tenocytes and collagen cross-linking require. Come back for a moment to that strange fact we opened with. Collagen fibers sitting quietly in the core of your Achilles tendon, some of them nearly as old as parts of your own body. There's something almost humbling in that. Your muscles are constantly being torn down and rebuilt, restlessly renewing themselves every few weeks of your life. But somewhere at your ankle, at the back of your knee, at your elbow, there's a rope holding steady, largely unchanged since some earlier version of you was walking around in it. It's not indestructible, and it's not indifferent to what you do with it. The matrix around it is very much alive, listening, responding, slowly rearranging itself in reply to how you load it, on a patient timeline that has nothing to do with how impatient you feel. Maybe that's the real reframe worth sitting with here. Getting stronger isn't always about building something new. Sometimes it's about learning to trust an old rope enough to keep pulling on it, carefully, consistently, and giving it the time it actually needs to hold you.